All right, class, in this lesson 4.1, we're going to take a look at graphs, puzzles, and map coloring. Actually, not so much the map coloring, but graphs and puzzles for sure. Here we've got graph terminology. Graph consists of a finite set of points. Finite means there's only so many. There's like 5 or 10, not infinite. And they're called vertices, and then lines called edges that join a pair of vertices. So certain types of graphs, of course, are called networks. So here our job is to see, can we take a picture like this and trace it? And trace means not lift our pencil. So in other words, trace means this. Whenever you see trace, you're assuming it means without lifting it up. So in other words, can I take this picture and draw it in such a way that I would not lift my pencil at all, and also not double draw on any particular line? And notice I just got stuck. Okay, so you can play with that. Let your mind think about that. Is there a way that I can trace this where I don't go back over a line? A line is called also a bridge, but is there a way that you can do this? So it's a fun little puzzle you can play around with in your own time if you want to push pause. I won't give you the answer yet until a little while after, but maybe you can figure it out for yourself if you want to draw it off the side. But I'm going to give it away at the end of the lesson here, so don't feel sad when I do that to you. Here, what's happening is we've got a place where, there's two different ways to draw this particular graph. Take a look at it. It's kind of weird, but notice there's this shape where A and C go together, and then C has to touch to E, E has to touch to D, but notice there's no vertex here at C and D. So there's a way, there's a way that you can bend and twist the same shape so that they don't actually show that they cross, because CB and AD are not actually, there's no vertex right here. Okay, so these graphs can be twisted and turned and manipulated. Your fun picture at the beginning can't, because they're all vertices, so don't let this get you too excited that there's a weird way of doing it. But it's just this is graph theory here. So one of the most famous problems, and yet they say elementary like it's easy. It's not easy. I had to stare at this problem for a while when I first saw it. Graph theory resonated in, not even going to try to say that word, Prussia during the 18th century, and the Pregel River divided, I think it's Königsberg, into 4 distinct sections as shown on this map. So here's what the picture looks like. Okay, and it was a popular pastime back then to just walk the bridges and see if there's a way that they could walk the bridges, each one exactly once, and return to their original starting problem. So this was just what people did apparently on the weekends. They just go for a walk and see if there's a way that they could go around here. Oh, can't do it. Go this way, come around, and see if they can walk it and end up not crossing the bridge twice somewhere. So they would try to figure this out. And then there was a very smart guy who actually came up with this picture, this graph of this situation. And I'm not going to spend too much time on that right now, but it does actually have these intersections as a way to draw this graph. So here we go. Let's keep talking here. We've got graph is connected if it is possible to travel from any vertex to any other vertex of the graph by moving along a successive edge. A bridge is a connected graph. In a connected graph is an edge such that if it were removed, the graph would no longer be connected. So notice these two shapes, these two triangles are connected by this bridge. And then here, this is separate. These are not connected shapes. So that being said, let's go back to the Königsberg Bridge problem. And notice the C represents the island C. And notice how many routes there are off the island. 1, 2, 3, 4, 5. And here there's 1, 2, 3, 4, 5 bridges off of this C. And then over here we've got A is this landmass. And it can go 1, 2, 3 different ways. So we've got 1, 2, 3 options here. And then here's B. So we've got 3 options, 1, 2, 3 here. So here's B, 1, 2, 3 options. And then lastly, land D. There's 1, 2, 3 ways to get off or on of land D. So that's how this graph came up from the actual topical graph. Okay, so let's take a look here at some more definitions. A vertex of a graph. This is very important because you're going to have homework questions about this. The graph is odd if the endpoint of an odd number of, if it's the endpoint of an odd number of edges. Similarly, it's even if the endpoint is of an even number of edges. So degree is a vertex of a vertex is the number of edges joined by that vertex. So let's look at this picture over here at A. Let's start there. This is an even edge because there is even vertex because there are two edges, two lines that touch it. C is odd because we've got 1, 2, 3 different edges that touch C. And then finally F. F is actually even because it has nothing touching it. And 0 is actually an even number. So that's what we've got here. Its degree is 0 because it has no edges to it. Its degree is 0, and 0 is an even number. So it's even. Okay, so another observation, wise man Euler, he's actually the guy that solved the bridge problem from earlier. He makes two observations here. He says, observation number 1, if while tracing a graph, if we neither begin nor end with vertex A, so in other words, if I go here and then keep going past it, then A has to be even. Okay, so it has to be even. If the graph can be traced, as we were saying before, so I was tracing it without lifting up my pencil, then it has at most 2 odd vertices. Then he actually furthers it and makes a theorem. A graph can be traced if it is connected and has 0 or 2. 0 or 2, very specific there. Connected and has 0 or 2 odd vertices. Okay, so let's go back to that original problem. And so I'm going to steal your thunder if and show you how this actually works, unless you figured it out already. So what you do is you count. I've got an odd, 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 odd vertex. There is 1 even vertex. C, 1, 2, 3, 4. So go back to his definition. It says connected. It is connected, has 0 or 2. We have 1 even vertex. Can this be traced? By his definition, no. It is not possible to trace this and not lift up your pencil and not overlap anything you already doodled, because any way you do it, you're going to end up having to go twice across a bridge. Okay, so now back to the bridge problem of that Prussia city where people will go out and have fun and try to do this. If you look at it, these are all odd vertices. There is no even ones. So, I'm sorry, I realized I just said even on the last one. There are 4 odd vertices. Now we read it and I still said even. A graph can be traced if it is connected and has 0 or 2 odd vertices, not even. I don't know why I said even. So here we've got 1, 2, 3, 4 odd vertices, and we can either have 0 or 2. And here we have 4, so that cannot be traced. Still the same answer, but a bad definition for it. Sorry. So here we have 1, 2, 3, 4 odd vertices. So can it be traced? Is there a way that this story can be done? And the answer is no. There is no way for that bridge to be crossed and traced in a way that you don't have to recross at least one bridge, because again, it has to be 0 or 2 odd vertices. And here we have 4, so it's not possible. Look at this shape. So we've got it looks good because we got 1, 2, so basically 1, 2 odd vertices, right? There's only 2 odd vertices, so it fits part of the definition, but the other part says it has to be connected. There's no way to do this because there's no way to get to F. It's just its own little island over there, all right? And then this one that we had, that shape that got unwound earlier, we've got only 2 odd vertices, and all the other ones are even. 1, 2, 3, 4, okay? So all of these other ones are even. So that means this figure can be traced. So if you really want to have fun, this one can be traced, the other one can't. Okay? Now this one, can this be traced? Well, let's take a look. Let's count. 1, 2, 3, 4, 5, 6. This is even. 1, 2, 3, 4. This one's even. 1, 2, 3, 4. That is even. 1, 2, 3, 4. That's even. 1, 2, 3, 4, 5, 6. These are all even vertices. So this shape, if you sat there and did it long enough, can be traced without lifting up your pen. I'm not going to sit here and show you the answer for it, but I'm just telling you it can be done. So we're going to take a look at this this picture of a city, and we're trying to figure out, is it possible to draw a graph that models the layout of this city where the vertices represent land masses and the edges represent bridges? And the way that to do that is to take your land masses and put dots on it, okay? And here we've got, these are bridges, okay? And this is a dot because we're all going to the bank. We're all going to this north bank. So basically you have 4 dots, okay? There's a bridge connecting them here, so that's one bridge. Then you've got 2 different bridges here, like that. And then you've got 2 bridges here. You got 2 bridges going down, and 2 bridges going down this way. So knowing that, let's take a look. We've got 1, 2, 3, 4. This is even. 1, 2, 3, 4, 5. This is odd. 1, 2, 3, 4, 5. This one's also odd. And then 1, 2, 3, 4. This one's even. So we have 0 or 2. We actually have 2 odd vertices, which means it is possible to draw to create or to trace this situation. It's possible to go from each bank and island and get around there to trace it properly without lifting up your pen. Okay. So here's a quick little picture, a little bit better diagram than what I doodled. So you can see this is odd, this is even, this is odd, and this one's even. So it is possible based on Euler's definition. Okay. So now you have a really hard problem. I feel it's hard, but it says find an optimal. Oops, sorry. I'm going to get there. Find an optimal, and it says Eulerization for the graph at the right. So here is your ugly bridge and vertices. And so Eulerizing the graph requires designing the optimal exhaustive route. So there is a best route to take with more than 2 odd vertices. So an exhaustive route is a route that travels along the edges of the graph and passes through each edge of the graph at least once. So this one's allowing us to go twice. An exhaustive route for a graph with more than 2 vertices will have to recross some of the edges. So this one's a little bit different definition. We're allowed to recross things, and we're going to have to actually add things. You're going to have options to add in vertices. So to create this Eulerization, we first have to identify in this picture where are our odd vertices, and here they are highlighted in red. This one's got 1, 2, 3 edges to it, 1, 2, 3. So you can see all of these that are highlighted red are all odd vertices, okay? Then our job is to figure out the fewest number of edges, called duplicate edges, so that all the vertices have the same even degree. There is no correct way to create a Eulerization. There are some methods that violate the cardinal rules. So it says only edges that are part of the original graph can be duplicated. And so what that means is I can't do what figure B is doing. I can't do this. I can't draw that in there. What we have to do is draw little triangle sides that show that there was already this blue line here, and I'm crossing it again. Crossing this one again. I can't do this where I'm jumping here and then going back. I have to go back and back again. Okay. So C shows the correct way to address adding edges between 2 non-adjacent vertices. So I'd have to go back and back again. Okay. So then it says the number of duplicate edges should be minimized. So figure A shows a graph with 4 odd vertices. The added edges in figure B are incorrect because there are extra edges that could be avoided. The duplicate edges in figure C shows the correct way to add edges between 2 non-adjacent vertices. Okay, so what we've got here is this can be bypassed. these extra parts right here, you didn't need to do this twice because I could have gone back, back, and then back around this way, and you've already got a way around this area. So there's two different ways I could go around, so that way this is extra drawing. So if you were to draw your way around this shape, there is a way to get back without having to do this extra information. Okay, so for our graph, the graph that shows the optimal Eulerization is shown below. Here was the original picture. Here's when I identified the odd vertices. And then here is our way to optimally Eulerize, to go in and do it. Now notice that there are not any extra diagonals. So your option is going to be multiple choice. You can automatically throw the ones away where there's like an extra random line that goes, I'll just draw a couple in here. So you're going to have one that, you know, they're going to do this and add in some extra little lines like that. If there was no original line in that area, then you can automatically throw that answer out. Okay? So that's going to get rid of most of your choices. And then you're going to have to kind of really stare at it. They're not that easy to really identify and pick out which was the best one, because there are two options that are probably going to work. It's just one's a little better than the other one. So kind of have to play with it, kind of look at it a little bit, and read through this example a little bit more to try to figure out which one for your one problem you have to work with is the best situation. All right, so again, biggest thing is that it has to be an extra loop where there already was one, and then you shouldn't have any unnecessary, so I don't want to have to go here twice or do any weird things where you're going around twice where you don't have to. All right, so good luck with this section. Let me know if you need any help through the Ask My Instructor feature of the lab.